Good morning. All right, guys, so today we're going to do a read along of an article on magma and its role in the rock cycle. I hope you did download the article so you can read along with me. And once you are finished with watching this read along, like I said, I'm going to ask you to do a write up of the article with the questions that I put on Google Classroom for you. So let's start. I'm going to be looking down a little bit because my computer screen's right below the camera, but read along with me, okay? So, magma's role in the rock cycle. Magma is a mixture of molten and semi-molten rock found beneath the surface of the earth. So molten means liquid or melted. So it's a mixture of liquid melted rock and semi, so sort of kind of halfway melted rock found beneath the surface of the earth. So then we have this picture of a lava lake. Now it's not really a picture, it's really sort of more of a computer graphic picture of a lava lake. And it says that on the rare occasions when magma breaks the surface, as in a volcanic eruption, it is called lava. This lava lake sits in Mount Nyiragongo, Democratic Republic of Congo. So what they're telling us there is that it's called magma when it's under the surface of the earth, but it's lava when it breaks the surface. So we did talk about that before, but that's just a little bit of nomenclature, a little bit of vocab. Okay, so let's start reading. Magma is a molten and semi-molten rock mixture found under the surface of the earth. This mixture is usually made up of 4 parts. Okay, so that's getting a little complicated. A hot liquid base called the melt, minerals crystallized by the melt, solid rocks incorporated into the melt from the surrounding confines, and dissolved gases. Okay, so that's a little bit more complicated than I would have thought. I thought that magma was just, melted rocks. So they're telling us that there's 4 different things. So let's learn a little bit more. When magma is ejected by a volcano or other vent, the material is called lava. Magma that has cooled into a solid is called igneous rock. So that's what we already learned about the rock cycle. Magma is extremely hot, between 700 degrees and 1300 degrees Celsius, which is 1292 degrees and 2372 degrees Fahrenheit. So that makes sense, right? Because to melt rock, you'd have to be super hot. This heat makes magma a very fluid and dynamic substance, able to create new landforms and engage physical and chemical transformations in a variety of different environments. All right, so that, I guess, I get that because magma does create mountains, right? That's how we get volcanoes. A volcano erupts, and then as the lava cools, we actually create a mountain, and that's how we get our volcanoes. The first time it erupts from the surface, and then the lava cools, we get a little bit of a mountain, and then the next time we get a little bit more, and it gets higher. The next time it gets higher, so that's how we get landforms. All right, so on the second page, how magma forms. Earth is divided into 3 general layers. The core is the superheated center. The mantle is the thick middle layer, and the crust is the top layer on which we live. Okay, so to stop there, we're actually going to talk about the layers of the earth in our next unit. So we'll get into a bit more detail on layers of the earth. It's going to be a couple weeks because we're going to talk about the rock cycle, and then, we are talking about the rock cycle, and then we're going to talk about minerals. So it's going to be a little bit, but we're going to get into a little bit more detail on layers of the earth in just a bit. So we'll learn about that in a bit. Magma originates in the lower part of the Earth's crust and in the upper portion of the mantle. Most of the mantle and crust are solid, so the presence of magma is crucial to understanding the geology and morphology of the mantle. So morphology means like how it's formed. Differences in temperature, pressure, and structural formations in the mantle and crust cause magma to form in different ways. Okay, so they're saying that there's different ways that magma forms based on where it is in the mantle and where it is and the different temperatures and pressures. And I guess that makes sense because if it's deeper in the mantle, there would be more pressure, it would be hotter. So if it's at a deeper place, more pressure, more heat. So let's look at the different ways. Decompression melting. Decompression melting involves the upward movement of Earth's mostly solid mantle. This hot material rises to an area of lower pressure through the process of convection. Okay, so let's stop there. What's convection? So convection means, have you ever heard when people say hot air rises? So that's what convection is. Convection is something that's less dense. We talked about density earlier in the year. So I'm sorry, you can see my cat behind me. That's what that is. So that's something less dense rising up, and something that is more dense falling down. So that's what convection is. So this hot material rises to an area of lower pressure through the process of convection. Areas of lower pressure always have a lower melting point than areas of high pressure. This reduction in overlying pressure, or decompression, enables the mantle rock to melt and form magma. Okay, so what they're saying there is that as the rock in the mantle, which is solid, as it gets it, so that convection current, it brings the rock up to this area of lower pressure, which has a lower melting point. And that means that since it has a lower melting point, that rock is able to melt and become liquid magma. Okay, so decompression melting often occurs at divergent boundaries where tectonic plates separate. The rifting movement causes the buoyant magma below to rise and fill the space of lower pressure. The rock then cools into new crust. So that means a divergent boundary, and again, we'll talk about this when we get to tectonic plates, which is our next unit. But a divergent boundary is where you have tectonic plates that are coming apart. That's what divergent means. For those of you who read the Divergent book series, divergent means coming apart. So where the plates come apart, the magma actually rises up and then cools when it comes towards the surface. Decompression melting also occurs at mantle plumes, columns of hot rock that rise from Earth's high-pressure core to its low-pressure crust. When located beneath the ocean, these plumes, also known as hotspots, push magma onto the sea floor. These volcanic mounds can grow into volcanic islands over millions of years of activity. So we know volcanic islands, right? That's how we have Hawaii. So what they're saying there is there are actually spots in the mantle where there's these volcanic plumes, where there's spots in the mantle where these volcanic plumes, these spots of magma just like shoot up through the ocean. And sorry. And when the magma comes through, the water cools it, so it hardens. And then more comes up and it hardens. And eventually enough of it happens that it gets out all the way up to the surface and it forms an island. That's, like I said, that's how we get Hawaii, the volcanic islands. Okay, so that's one way, decompression cooling. So let's look at transfer of heat. Magma can also be created when hot liquid rock intrudes into Earth's cold crust. As the liquid rock solidifies, it loses its heat to the surrounding crust. Much like hot fudge being poured over cold ice cream, that sounds delicious, this transfer of heat is able to melt the surrounding rock, the ice cream, into magma. Okay, so essentially what they're saying there is that if you have really hot magma and it's being poured onto regular rock, that is going to melt the regular rock and form more magma. Transfer of heat often happens at convergent boundaries, where tectonic plates are crashing together. As the denser tectonic plates subduct or sink below, or the less dense tectonic plate, hot rock from below can intrude into the cooler plate above. This process transfers heat and creates magma. Over millions of years, the magma in this subduction zone can create a series of active volcanoes known as a volcanic arc. All right, so what they're saying there is, remember we said divergent boundary means the plates coming apart. So a convergent boundary is where the plates are coming together and one's going under the other one. So at that kind of boundary where one's going under the other one, what they're saying there is as one's going under the other one, they can actually have the plates are coming together, and as the plates are coming together like this, you have the hot rock from underneath. So the magma underneath is essentially coming up, and as it's coming up, it's actually transferring its heat, because this rock underneath is magma. It's very hot. It's transferring its heat into the rocks up above, and it's actually starting to melt this rock up above. So you have this boundary here where there's a little crack here because there's a boundary between the plates. So this rock is actually, this magma underneath is transferring its heat into this crack between the plates, and it's creating a sort of, there's a little crack here, and it's creating a sort of ring of volcanoes because there's a crack here where that magma can transfer heat up, and it's creating a ring of volcanoes. That's that volcanic arch or arc. All right, so let's look at flux melting. Flux melting occurs when water or carbon dioxide are added to rock. These compounds cause the rock to melt at lower temperature. This creates magma in places where it originally maintained a solid structure. Much like heat transfer, flux melting also occurs around subduction zones. In this case, water overlying the subducting sea floor would lower the melting temperature of the mantle, generating magma that rises to the surface. So this is saying that if instead of having land where the plates are doing this, you have plates that are doing this, but it's under the water. So if you have plates that are doing this and there's an ocean on top, you have water or carbon dioxide, but water or carbon dioxide over top, and that allows the rocks to melt at a lower temperature. And in that case, you have essentially magma that can form at a lower temperature because the rocks can melt at that lower temperature. So in that case, it's sort of similar to what happened before. It's just what happened before happens at a lower temperature. And so in that case, you basically get the same thing that happened in the one before, just in the ocean. Okay, so let's look at magma escape routes. So we've talked about how magma forms. How does it come up to the surface? Magma leaves the confines of the upper mantle and crust in two major ways, as an intrusion or as an extrusion. So let's talk about what those are. An intrusion can form features such as dikes and xenoliths. An extrusion could include lava and volcanic rock. Magma can intrude into a low-density area of another geologic formation, such as a sedimentary rock structure. Oh, okay, sedimentary rocks are getting a little deeper into the rock cycle then. When it cools to solid rock, this intrusion is often called a pluton. A pluton is an intrusion of magma that wells up from below the surface. Okay, so thus far we haven't really defined intrusion, so let's take a step back and define that word. So intrusion is a word that we might actually be familiar with, right? So to intrude on something, it means like to interrupt or like to sort of go into something that you're not a part of. And that's actually what it means here. So an intrusion of magma means that the magma is sort of like going into something that it wasn't a part of. So an intrusion can form features such as dikes and xenoliths. Dike, by the way, is the word for dam, meaning like something that stops water. Just putting it out there for those of us that are being immature right now. Okay, so, and an extrusion means the opposite. So instead of like intruding into something where it's not supposed to be, including lava and volcanic rock, in other words, like almost like an explosion. So an intrusion is going into some place where it's not supposed to be. An extrusion is like an explosion. Okay, so let's go back. Magma can intrude into a low-density area of another geologic formation. In other words, it's like there's another geologic formation, like a sedimentary rock formation, and the magma is like sneaking in there. Okay, when it cools to solid rock, this intrusion is often called a pluton. So a pluton is when you have a sedimentary rock formation and the magma like sneaks in there and then cools. A pluton is an intrusion of magma that wells up from below the surface. Plutons can include dikes and xenoliths. A magmatic dike is simply a large slab of magmatic material that has intruded into another rock body. So, a magmatic dike is essentially when you have magma that sneaks into another rock formation and then cools down. A xenolith is a piece of rock trapped in another type of rock. Many xenoliths are crystals torn from inside the earth and embedded in magma while the magma was cooling. So that's kind of cool. So they're like crystals, and then when the magma cools, you can actually like chip it away and see the crystals. The most familiar way for magma to escape or extrude to Earth's surface is through lava. Lava eruptions can be fire fountains of liquid rock, that's what you usually see in the movies, or thick, slow-moving rivers of molten material. That's what usually happens in real life. The whole like explosion thing doesn't usually happen in real life. Lava cools to form volcanic rock as well as volcanic glass. That's that obsidian that I was telling you about. Magma can also extrude into Earth's atmosphere as well as part of a violent volcanic explosion. This magma solidifies in the air to form volcanic rock called tephra. In the atmosphere, tephra is more often called volcanic ash, and it looks almost like papery. It does look like ash. As it falls to Earth, tephra includes rocks such as pumice, which if you've ever gotten like a pedicure, they use it to like get the dead skin off your feet. Magma chamber. In areas where temperature, pressure, and structural formation allow, magma can collect in magma chambers. Most magma chambers sit far beneath the surface of the Earth. The pool of magma in a magma chamber is layered. The least dense magma rises to the top. The densest magma sits near the bottom of the chamber, and that makes sense if we think back to what we know about density. Remember, we did a few density experiments. The densest thing would sit at the bottom, and the least dense thing would rise to the top. Think back to what we did about density. Least dense thing floats. Most dense thing sinks. Sorry, I can't talk today. Over millions of years, many magma chambers simply cool to form a pluton or large igneous intrusion. Remember what pluton means? That's that thing where the magma sneaks up and then cools. If a magma chamber encounters an enormous amount of pressure, however, it may fracture the rock around it, which makes sense. Magma chamber is like a big pool of magma. If there's pressure on it, it would fracture, break the rock around it. The cracks, called fissures or vents, are telltale signs of a volcano. Many volcanoes sit over magma chambers, which makes sense. If you have a pool of magma and there's a lot of pressure on it, wouldn't that be maybe the making of a volcano? As a volcano's magma chamber experiences greater pressure, often due to more magma seeping into the chamber, the volcano may undergo an eruption. An eruption reduces the pressure inside the magma chamber. As long as more magma pools into a volcano's magma chamber, there is the possibility of an eruption, and the volcano will remain active. So, for volcanoes to remain active, more magma has to keep going into the chamber so that the volcano can erupt and form more igneous rock. If more magma doesn't keep going into the chamber, then the volcano can't erupt anymore, so it couldn't be active. Large eruptions can nearly empty the magma chamber. The layers of magma may be documented by the type of eruption material the volcano emits. Gases, ash, and light-colored rock are emitted first, from the least dense top layer of the magma chamber. Dark, dense volcanic rock from the lower part of the magma chamber may be released later. So that's going to be from the bottom of the magma chamber because, again, the least dense is on top, so that's going to go first, and then the most dense is at the bottom, so that will go last. In violent eruptions, the volume of magma shrinks so much that the entire magma chamber collapses and forms a caldera. And a caldera, essentially, it looks like, caldera means cauldron. So a caldera actually looks like a cauldron because the magma chamber actually collapses on itself because it's empty. All right, so let's look at types of magma. All magma contains gases and a mixture of simple elements. Being that oxygen and silicon are the most abundant elements in magma, geologists define magma types in terms of their silica content, expressed as SiO2. These differences in chemical composition are directly related to differences in gas content, temperature, and viscosity. Viscosity means how much it flows. So think about like water and like pancake syrup. So water flows more easily than pancake syrup. So that means that water is less viscous than pancake syrup. So that's what viscosity means. It's how easily it flows. Okay. Mafic magma. Mafic magma, say that 3 times fast, that's hard to say. Mafic magma has relatively low silica content, roughly 50%, and higher contents in iron and magnesium. This type of magma has a low gas content and low viscosity, or resistance to flow. Mafic magma also has high mean temperatures, between 1,000 and 2,000 degrees Celsius, or 1,832 degrees and 3,632 degrees Fahrenheit, so hot, which contributes to its lower viscosity. So that means it flows pretty easily. So it's thin, it flows really easily, so it'd be kind of like watery almost. Low viscosity means that mafic magma is the most fluid of magma types. That's what I was saying, it's like fluid, it's like watery. It erupts non-explosively and moves very quickly when it reaches Earth's surface as lava. This lava cools into basalt, a rock that is heavy and dark in color due to its higher iron and magnesium levels, which makes sense. If you think about iron, iron's a heavy metal. So if the rock has a lot of iron in it, it would be heavy. Basalt is one of the most common rocks in Earth's crust, as well as the volcanic islands created by hotspots. The Hawaiian Islands are a direct result of mafic magma eruptions. Steady and relatively calm lava fountains continue to change and expand the big island of Hawaii. So it makes sense, if that's the most common type of eruption, and that's how volcanic islands are formed, it would make sense that that's the most common type of rock that you find there. Intermediate magma. Intermediate magma has higher silica content, roughly 60%, so that's more than mafic, right? Mafic had 50, than mafic magma. This results in a higher gas content and viscosity. So that means it's not going to flow as easily, it's not going to be as liquidy. Its mean temperature ranges from 800 degrees to 1,000 degrees Celsius, so it's not quite as hot, which I guess makes sense, right? Because the hotter something is, the more liquidy it's going to be. And that's 1,472 degrees to 1,832 degrees Fahrenheit. I mean, that's still really hot, but still, it's not as hot. As a result of its higher viscosity and gas content, intermediate magma builds up pressure below the Earth's surface before it can be released as lava. This more gaseous and sticky lava tends to explode violently and cools as andesite rock. Intermediate magma most commonly transforms into andesite due to the transfer of heat at convergent plate boundaries. So remember, that's where the plates are coming together. Andesitic rocks are often found at continental volcanic arcs. So remember, that's where you have all the volcanoes in a ring, such as the Andes Mountains in South America, after which they are named, right? Andesite rocks, Andes Mountains, so that's what they're named for. That's where they were discovered. All right, and felsic magma. So felsic comes from the word that iron is based off. So iron is also called ferrous. So I'm assuming it has a high iron content, but let's look. Felsic magma has the highest silica content of all magma types, between 65 and 70%. Remember that mafic had 50 and the intermediate had 60, so this has the highest. As a result, felsic magma also has the highest gas content and viscosity and the lowest mean temperatures, between 650 and 800 degrees Celsius. So yeah, it's going to be like not real liquidy at all. That's 1,202 and 1,472 degrees Fahrenheit. Thick, viscous felsic magma can trap gas bubbles in a volcano's magma chamber. These trapped bubbles can cause explosive and destructive eruptions. These eruptions eject lava violently into the air, which cools into dactite and rhyolite rock. So that rhyolite rock that's the example of the igneous rock that I showed you the other day. Much like intermediate magma, felsic magma may be most commonly found at convergent plate boundaries, so that's the ones where they're coming together, where transfer of heat and flux melting create large stratovolcanoes. And we'll talk about what stratovolcanoes are when we talk about types of volcanoes, but for right now, stratovolcanoes are the kind that they erupt, they create a layer of lava, and then next time they erupt, they create another layer, so they keep getting higher that way. Mysterious magma. Magma is usually studied as lava or igneous rock, probably because it's really hard to get under the surface of the earth, so we can't really do it. So we have to study what's on top. But most magma remains molten or partly molten beneath Earth's surface. In fact, magma has only been discovered 3 times in its natural habitat deep in Earth's crust. Geothermal drilling projects discovered 2 magma sites on the Big Island of Hawaii and 1 on Iceland. Tapping into magma's potential. In 2009, the Icelandic Deep Drilling Project created a well that uses magma to generate geothermal energy, which would be awesome because if we could use geothermal energy from magma, I mean, it's so hot, we could power like everything. Normally, geothermal energy is created by pumping water into hot volcanic bedrock, creating steam that is then harnessed to generate electricity. While normal geothermal sources average around 60 to 80 degrees Celsius, 140 to 176 degrees Fahrenheit, the magma well's steam reached a record-breaking temperature of 450 degrees Celsius, which is 842 degrees Fahrenheit. And think about how hot those different types of magma were that we read about just a minute ago. They're like hundreds, even thousands of degrees hotter. So if we could harness that, that'd be amazing. This huge increase in temperature allowed just one magma well to generate roughly 36 megawatts of electricity, powering 36,000 homes. 36,000 homes. And again, actual magma is like thousands of degrees hotter. In comparison, one single wind turbine generates between 1 to 3 megawatts. So it's like 36 times more. It's crazy. Hawaii's molten magma. Hawaiian magma is different than magma in other parts of the earth because it has more molten rock and less dissolved gases and rock fragments. The Hawaiian volcano Kilauea on the Big Island of Hawaii has erupted with enough molten lava to pave a road around the earth 3 times. It's crazy. All right, so that's the end of the article. I know it was a long one, but it's got a lot of really interesting information. So first of all, it talks about magma's part in the rock cycle in creating igneous rocks and also how it affects sedimentary rock formations. But it's also got a bit of information on tectonic plates and layers of the earth, which is our next unit. So I thought that was kind of interesting and something to look forward to, plus some information on energy production. So a bunch of information that we're going to look at in future units, so a little sort of teaser for those. I do want you to now go to the Google Classroom write-up, start doing that, and I look forward to seeing your write-up, and I do look forward to seeing what you found most interesting about this article because I thought there were a bunch of kind of cool tidbits of information in here. I will talk to you guys later, and we will talk about rock cycle, and we're going to start mineral testing as well next week. Okay, I'll see you guys later.